Hello guys, welcome to our YouTube channel vlsichaps, and we are back with another interesting video. Previously we talked about various kinds of microprocessors, what it consists of, what are the real life applications of the microprocessor and how they works. Now, if we talk about a more customized and improved version of microprocessor, then it will lead us to the microcontroller. So let's understand this how. In processors, previously we understand that on a single chip, just the processor is embedded. All the other peripheral units like input-output ports and memory units that we need to connect it externally with that particular chip in order to make that particular microprocessor function properly. Now in case of controller, all the three units, the processor, memory units and the input-output ports, all these three will be embedded on a single chip. So microcontroller is an integrated electronics computing device which includes not just the processor but much more elements within that. So as you can see on the screen, CPU along with the CPU controller also handles various memory units, input output ports, various watchdog timers and counter mechanisms, pulse width modulation in order to have real time frequency changes, analog to digital and digital to analog converters to convert the human readable analog input into a discrete or digital input and vice versa. It also gives serial interfaces support to communicate from one block of the controller to the another block serially. Microcontroller also has its core functionality of clock by which it is able to perform all the other functionalities or tasks. And to provide this clock, it will have various oscillators of various frequencies. So using this clock, the flip-flops within that particular chip or the controller will be able to know the state of change of various signals, and by that way they will be able to make the decision when to perform what. Also they have on-chip debugging facility by which we will be able to debug our code on live hardware without removing chip outside. Controller also support various buses by which data communication is happening. So let's understand all these or most of these elements in a very detailed manner. So let's talk about first memory. So we know that we have two different kinds of memory. One is volatile, another is non-volatile. But also we have special kind of memory which is called flash memory. So volatile memory is what? Temporary storage elements. We will have the data stored in that particular memory unless and until the device is powered up. Once the power is off, the data will be flushed out. In that we have two kinds of memory, RAM, random access memory, and the CPU registers. In random access memory, we have further two kinds, static and dynamic RAM. The static RAM will have various kinds of flip-flops and transistors to store the particular bit. So it will have a structure of 4 or 6 flip-flops which will be able to store one particular bit. They use quite a space, but the latency is very low, so they are fastest that we can access. On top of that, the dynamic RAM will have transistors and capacitors. So capacitor will be charged and get discharged, and accordingly the state of that particular bit will be decided, either it's 0 or 1. So here we are using the capacitor, so because of that we need to refresh this dynamic RAM periodically because the charge in that capacitor will get degraded over the period of time. But this dynamic RAM can store multiple bits. It has very wide and dense storage capacity. But again the latency is high. So there is a controversy between these two. Based on our type of application we can use likewise. If we talk about CPU registers, then basically they are used to store the intermittent results which a processor has derived. So we will have two registers, one is general purpose and the second is special function. General purpose registers will store the outputs of arithmetic and logic units, the intermediate results, while the special function registers will store the state of the program. like program counters, instruction pointers, stack pointers, which are very critical to handle and store. If we talk about non-volatile memory, then this memory will have a permanent storage. Even if the device is powered off, we will have our stored content. So we know that read-only memory is very well known non-volatile memory. But apart from that, we have electrically erasable programmable memory. So in ROM, once the program is done in that memory, we cannot rewrite it. While in EEPROM, E2PROM, we have that functionality called electrically erasing. While where we are using uh, electrical methods to erase the content and rewrite it. But that mechanism, that procedure is quite costly and lengthy. We are using ultraviolet lights to erase the content here. If we talk about the flash memory, then flash is nothing but the combination of volatile and non-volatile. The reason is it has that ROM capability that once programmed, we cannot reprogram it unless and until it's required. But also, flash memory is the fastest accessible, which also has the property of RAM. So we can have both the characteristic of RAM and ROM, and which is why flash has become widely used. In our cell phone, we have mostly the flash memory. Now let's talk about various ports. So in microcontroller, we have input and output pins. So basic function of these pins are to give the input to control something, some interface, or to get the output or monitor something based on the external events triggered. So to give input to any microcontroller pin, we need to define it as an input pin. And to get the output from that microcontroller pin, we need to define that as an output pin. So for that, we have various characteristics of this input modes and output modes of these pins. So if we talk about the input modes, then we will have one floating point mode. So the thing is here, the default state of this pin won't be determined, won't be defined. It is called a tri-state where the default state of the pin is undefined unless and until any external event is triggered. It will have a certain state, either high or low. As you can see in the screen, the state of S1 is not defined yet, the port which is open. Once I switch it back, the LED will turn on and the whole loop will get completed, and that's how it will have a state, particular state. So this is called a floating point of input mode. If we talk about the pull-up mode, then here we will have a defined state. The defined state will be high because the GPIO pin will directly drive the power from the VCC, as you can see here. Once any external event is triggered, here the push button is an external mechanism. Once I trigger the push button, the path will be completed to from VCC to ground, and this pin will be finish the path. So it is called pull up because the initial state is high. Likewise, if we talk about pull down, then its initial state will be low. It will directly fetch the power from the ground. It will have low state by default. Once I push the button or external event is triggered, it will finish this loop from VCC to ground and get the whole state complete. If we talk about repeater mode, then this repeater will behave as in pull up and pull down as and when required. So by default, it will hold the previous state. If I want to configure a certain pin as in pull up and pull down at the same time or real time, I can define its mode as in repeater. If we talk about hysteresis, then this is a very special kind of behavior of particular pin. You know, we have experienced that whenever I push or pull the button, at very micro seconds or micro period of time, there is not a defined state of that button, either it's high or low. We will have that this kind of various waves in between, which is called a spurious response of particular event or button. or can say the shaky power. So to define that at which voltage level this particular pin will define input high and input low state, for that we will have this hysteresis kind of mode. In that user will be able to define various high voltage and low voltage threshold, by which it will be able to decide that okay, above this high voltage I'm supposed to call it as logic 1, and below this low voltage I am supposed to call it as logic 0. So based on various controller vendors we will have this threshold voltage defined. You can also check that out in specific datasheet of that particular microcontrollers. If we talk about the output modes, then we have one push pull kind of pin. In this, that particular output pin will drive the output either 0 or low based on the input that it is provided. Here it is consist of two different MOSFETs, PMOS and NMOS. So if I give logic 1, then output will be logic 0. So it will drive the output to the low. If I give logic 0, then it will give output as in logic 1 and drive the output as in high. So by this way it can be configurable either 0 or high based on whatever the input it's provided. If we call about open drain pin, then it will have the drain output as in open. Previously based on 0 or 1, we were able to get a specific state 0 or 1. In this case, if we give 0, then it will not have any specific state. If we give 1, then it will drive this power to 0. So what happens that irrespective of 0 or 1, this drain will continuously be open. What is the use case here? When we want to check each and every output of this pin, or we want to check a specific event that is being executed on each and every pin or not, we can use those pins as an open drain. The reason is these pins are not giving any effective output when it's applied as a zero logic. So in case whenever the power is down or any power failure is happening, or by anyhow this input state of that pin is below this threshold, the certain voltage low level, it won't affect the output. But if we give the power 1, or unless and until they are powered up, they will give a certain signal which is logic 0. So that is how they can be used. Also we have a high drive mode of the output pins which drives the high power, which is able to drive high current. They are basically push pull mode of pin, but in push pull they are able to drive around 8 milliampere currents, while in high drive we will be able to drive 40 milliampere around of current, which is used in very high kind of applications. Now let's talk about further. We will have timers, counters, and watchdog timers, also pulse width modulators as a part of our microcontroller system. So what are the timers? Consider an example that we want to blink a particular LED for 5 seconds. After that 5 seconds, that LED should be turned off. So for that we need to configure a timer in microcontroller. And how we will do that? So for that our clock in the microcontroller will come into the picture. Let's say our microcontroller have 5 megahertz of clock. So in 1 second it will generate 5000 pulses. So if we want to keep that particular count as 5 seconds, then I need to have 25,000 of pulses of clock. So I can write an algorithm that once the counter of 25,000 pulses will reach, I will have 5 seconds of delay. And by that way, I can perform the next task, which is to turn off the LED. So this is how timers and counters, they both combine together and work as a particular outcome. Also, the another important item, or can say the use case of counters, is that to identify how many number of external events has been done. Another another example of it is like, let's say I want to count number of person that pass through a particular gateway. For that, I have IR sensors. So that IR sensors will detect the motion or the object that goes around it, pass through it. So what I will do is I will have a particular pin which I will continuously monitor. That once person passes through that particular sensor, that pin will give a certain output. Let's say if it's giving a logic high. So I will count how many numbers of logic high that I am receiving at certain period of time. The number of logic high that I will get, based on that I will increment a particular counter or the register, and based on that I will be able to identify that okay, these numbers of persons are have been passed through that particular gateway. Another example of a watchdog is that it the name itself suggests that it is kind of security mechanism. We have watchmen at our home which provides the security of the house. Just like that, this watchdog timer will provide the security to our controller. How we will do that? So in that watchdog timer, it will have a specific timeout period. Every time that timeout will reach, microcontroller will kick that watchdog by again resetting it to 0 and again counting back to the timeout. If microcontroller in any case couldn't be able to perform that kick operation, that resetting the timer of watchdog, that means watchdog will be able to know that there is something wrong with the microcontroller, or microcontroller functionality is not working properly. It is supposed to do this kicking out operation at certain period of time, but it is not able to do that. And that is how watchdog will give a reset signal to microcontroller. So it will reset the whole board and again restart its functionality. So this is very critical and important feature of the controller, which is watchdog timer, and which is used very widely and in all the critical operations. The another feature of microcontroller is pulse width modulation. Here the name itself suggests that we will have various pulses whose width can be modulated, whose width can be changeable at real time. So we will be able to generate a continuous pulse with preset duty cycles. So we will have a fixed width of these signals. But as and when required in real time, we will be able to change the width of these signals, and we will be able to change the frequency. And if we change the frequency, then we will get the variable number. So the use of this PWM is in speed controller, where the speed is changing real time in various ways. So this is how the microcontroller provides various features and the support of various units. So if we talk further about peripherals in microcontroller, then we have analog to digital converter, digital to analog converters, and serial interfaces. Now analog to digital converter comes into the picture where we need to convert an analog or continuous signal into a discrete or digital form. We know that controller understands the only language which is binary in terms of zeros and ones. So if we provide any signal which is in analog form, which is in human readable form, in order to understand that signal, in order to process that signal, we need to convert that signal into the digital or discrete ones in which a processor will be able to handle. For that, we need analog to digital converter. The example is voice recorder, where we give input as an analog signal or human readable signal, and the output is in terms of discrete, where the processor is handling. If we talk about digital to analog, then the opposite mechanism is performed. Here, the digital signal will be converted into the human readable or analog form. The reason is when controller is supposed to provide an output in terms of human readable form, at that time this digital to analog converters comes into the picture, because they processed the output signal inside the controller will be in terms of discrete or digital. But in order to understand us, they have to convert it into the analog one. The best example is all the sound equipments like speakers, earphones and all. So if we talk about various interfaces, then microcontroller have serial interfaces, which allows one block of the unit or controller into the to talk with the another unit serially. So the data is being transmitted serially in two forms. One is the synchronous and another is asynchronous. Now let's understand the difference first. In synchronous, both the transmitter and the receiver will have a single clock. So based on the clock, whatever the data that transmitter is transmitting will be in terms of frames, single frames. So once the frame is transmitted, the same frame will be received at the receiver end because both transmitter and receiver are sharing the same clock frequency. The rate at which transmitter is transmitting, the same rate receiver is receiving. So there won't be any data loss. So at the receiver end, we don't need to add any algorithm or functionality by which receiver will be able to know that okay, this is the start of the frame and this is the stop of the frame, because each and every bit in that frame will be passed with one single clock pulse. And as the clock pulses are synchronized with transmitter and receiver, they will get the data in synchronized manner without any loss. The best example of this synchronous transmission is where the time critical operations are performed, like in video streaming or in voice typing or in calls, where transmitter or receiver both the ends should be in sync. There shouldn't be any delay. Otherwise, the functionality will get corrupt. If we talk about the asynchronous, then there is not any clock functionality at all. The transmitter will transmit the data in terms of bits or chunks of the bits. So whatever the transmitted data is there, in order to receive those data, there should be some functionality or mechanism by which receiver will be able to know that okay, this is the start of the bit of this whole chunk, this is the stop bit of that whole chunk, and this is how I'm getting this whole frame. So for that, we need to add some algorithm or functionalities in order to identify that this is the start bit, this is the stop bit, and this is the parity bits and all. The example of this asynchronous transmission is day-to-day emails that we receive or the programs that we perform. So where the clock is not required and the time criticality is not that important. Now let's talk about the further peripherals which microprocessor is supporting. Microcontroller also provides on-chip debugging facility. So what happens is whenever we want to debug any program which is flashed into the controller, we don't need to pull that specific processor or controller out and we need to debug it. We can debug the same using on-chip debug mechanism embedded within that particular chip. We don't need to flash that out. And by that we will be able to do the inspections of various internal states or the variables, and we can perform this functionality by using various breakpoints and watch points and see how the particular program behaves within that particular live hardware. Also microcontroller supports various interrupt functionality, which is very important and very major task that each a microcontroller supports. That is one signal which is emitted by the hardware or software whenever any event is supposed to require an immediate or critical attention. So that particular signal we can generate either by using software, using instructions, or we can trigger any external event or make any external hardware to generate that event, by which controller will be able to know that something critical has arrived. I am supposed to stop all the current execution of the tasks and I am supposed to give attention to that particular event. Also, microcontroller provides low voltage disconnect functionality, which prevents injuries from high voltage or critical shock to that particular device. So whenever any high voltage or shock sort of mechanism happens within that controller, it won't damage the whole controller, but we have that shield functionality of low voltage disconnect where it will secure the power module of microcontroller and will uh, stop the module to get damaged. Using power on reset functionality, we will be able to offer a last resort in case of any sudden system crash. So if in between our system stopped working or got hanged or went into a state where it's continuously doing the same task again and again in loop, then we can have this power on reset functionality. So whenever that reset button we press, the controller will stop executing all the tasks and restart it as if it is fresh board. So by this way, we will be able to uh, make sure that processor is working properly or controller is behaving again properly. So these are various peripherals that we talked about, and each and every peripheral has its important role in various tasks or functionality. So that is all, guys. Let's make the most with our channel VLSI Chaps. You can be the part of our core team contending creating content. You can contact @max_chap on Telegram. You can also learn VLSI better by using our YouTube channel videos. So please do like, share and subscribe our channel. You can have all the information or the question answers or material on our website www.vlsichaps.com. You can also interact with the students and other members in our Telegram group, which is @VLSI You can also follow us on our Quora space where we post various blogs on recent electronics topics. You can refer that. You can also ask questions there and get the answers. So we are on Quora, FB, Instagram, LinkedIn, and Twitter, and various other mediums. Thank you, guys. Thank you for watching this video. Please do like, share, comment, and subscribe. See you in the next one. Goodbye.